All right, if you do have any questions, just let me know and I'll go through it. I'm trying to do the recording at the same time, so if you do see the double screen, just let me know. Okay, so today we're going to be looking at different types of intermolecular and intramolecular bonds. We're going to look at how this associates in terms of their physical properties of elements and physical properties of compounds. Okay, so we're going to investigate similarities and differences with inter and intra, and then we're going to also look at explaining some physical properties that they have. Okay. All right. So last lesson we talked about the different types of structures like ionic, covalent, and the type of lattice structures you create. So you have covalent molecular, um, metallic structure, ionic, covalent network. These are just like a little step-by-step guide in terms of how you can identify which one's which. So let's say if the substance is a liquid, okay, at room temperature and pressure, if that's yes, then it's definitely a covalent molecular compound. What we mean by covalent molecular compound, a very simple covalent structure, so something like O2 or carbon dioxide. These are examples of covalent molecular compounds. Okay, so they don't really get larger than a couple of elements binding together. Does it does the solid melt easily? If it does, that's also a covalent molecular compound. Does it conduct electricity in its solid state? So anything that conducts electricity at its solid state is a metal. Okay, so any metallic structure should conduct metal as a solid. Does it conduct electricity in its molten or aqueous state? So that's a lattice, ionic lattice. An example of an ionic lattice would be sodium chloride, so table salt. Okay. Next one we have is, does it have a very high melting point? If it has a really high melting point, then you have a covalent network. Now the covalent networks that we looked at was graphite, and the other one we looked at, let's see if I can write on this. The other one we looked at was diamonds. Oh, no, that doesn't really work. So the other one we talked about was diamonds. Graphite is 3 carbons bonded together, while as just give me a second. While as diamond is 4 carbons bonded together. So that's kind of the difference between those two there. So if I just draw it back up, so graphite, if you recall, is 3 diamonds bonded together, whilst diamond is 4 carbons kind of bonded together and all that. So connected to 4 carbons. Okay, so there's that. If you look at, I'll show you this simulation a little bit later, but if you actually have a look at this simulation later on, when you heat up, let's say a gas or let's say water, what you will see is these particles will move further and further away from each other. What we're doing here when it comes to boiling, we're breaking intermolecular bonds. So it's bonds between compounds, bonds between molecules. We do not break intra, so bonds between elements. That's not what boiling does. Okay, we talked about this last lesson. We had intra, it's the bonds between the elements, and inter, the bonds between the molecules and the compounds. Okay, so the bonds between molecules are weaker. So if you do have a weak intermolecular bond, that will affect the overall melting point and boiling point of the lattice. Okay, Remember, when you boil something, you're really just trying to separate this bond from each other. So the stronger this bond is, the more energy you require, which is why strong intermolecular bonds lead to a high melting point, a high boiling point. Okay, so just some definitions, intramolecular bonds and also intermolecular bonds. Just describing what they are between each other, and that's sort of your little depiction of where to find them on a chemical structure. Okay. All right. So the three major intramolecular bonds we talked about was metallic bonding. Okay. Bonds between positive metal ions with a sea of delocalized electrons moving around it. We had ionic bonds, so a bond between a metal plus a nonmetal. And this is where the nonmetal takes up all the share of electrons from the metal ion. The last one we have is covalent bonds, and these are bonds between two nonmetals, and basically the electrons are shared between both. Okay. The way we determine the difference between a covalent and an ionic bond is through electronegativity. Okay. Electronegativity is the ability an atom has to attract bonding electrons towards itself. What do I mean by bonding electrons? I really only mean things like the valence electrons. The reason why I'm saying the valence electrons because these are the electrons that are most likely are going to be displaced from the atom and it's going to be traded away. Now, electronegativity, the trend works in this way. The further down you go on the periodic table, the weaker the electronegativity is. As you can see, francium has a electronegativity of 0.7. The strongest or the highest value for electronegativity comes in fluorine here. Okay, so fluorine has a electronegativity of around about 4, according to this little chart here. And so that's what we get. Okay. So if it's an ionic bond, not only is it usually between a metal and non-metal, but the electronegativity difference should be greater than 2. So if you have a difference bigger than 2, like we have here with sodium and chloride, so it's a difference of about 2.23, then that means it's an ionic bond. If it's covalent bonds, anything smaller than 2, right, technically would equate to a covalent bond. So a bond between nitrogen and oxygen would equate to about a difference of 0.4. So that's really good. We did talk about the issue of what if there's that little in-between spot, the 1.5 to about 2 to maybe even 1. In between this gap, okay, what's really happening to electrons? Because if you have one extreme where all the electrons are being taken away, and the other extreme where all the electrons are shared equally, then there has to be some kind of in-between spot that is happening as well. And that's what polar covalent bonds are, okay? Polar covalent bonds is still covalent, okay? Still covalent. However, instead of having equal shares, so something like a pure covalent bond, which is just equal amounts of electrons. A polar covalent bond is where one particular atom will take more electrons than the other. So they're still sharing, but it's not equal anymore. So it's unequal sharing of electrons. Okay? And this has a little side effect to it as well. So a polar covalent bond, okay, leads to uneven sharing of electrons. What happens is if one atom has more electrons than the other, okay, technically that makes that side slightly or partially more negative, okay? So delta here, delta minus means it's a partial negative charge, okay? Delta plus means it's a partial positive charge, okay? So these aren't charged particles, so these aren't cations or anions. They're simply elements that have a slightly negative or a slightly positive charge. And that's what a polar covalent bond is. Now, a famous example of a polar covalent compound, you drink it every day, you need it every day, H2O. Okay? Water is an example of a polar covalent compound. That's why water is really good at dissolving ions such as table salt. But we'll get into that a little bit more as well. All right, the next we have is just this. So just a little demonstration of what these mean. Okay, so what we have here, these are called your partial charges. Okay, so these are partial charges. These are not particles, so they're not ions, so they're not charged particles. Okay, what you can also see here is if I try and draw it out in terms of electron density, maybe I'll use a light blue color. So we know that hydrogen is less likely to attract electrons towards itself, and then chlorine is more likely to do that. So what you would actually see in the bond is chlorine. If I try and draw the electron cloud, chlorine would be more focused, so a bit bigger, and then hydrogen would be a bit smaller. Okay, so this is what we mean by electro or delta negative, as in there's a greater electron cloud next to the chloride. Okay, when we establish a situation where one side is more positive, one side is slightly more negative, we get a thing called a dipole. A dipole is essentially having a positive end, a negative end. Okay, that's how we use it in chemistry. All right. Now, not all sort of compounds can be quantified or identified as polar or non-polar. So you can have a situation if the compound is symmetrical, okay, it will be non-polar, meaning there's no partial charges. If it's asymmetrical, then the molecules are polar. And what do I mean by that? Have a look at these images at the bottom here. Okay, you have water, you have hydrogen. Now there is a difference in polarity, okay, between hydrogen and oxygen. But at the same time, the molecule is not symmetric. Basically, what I'm trying to say by symmetric is water is bonded to hydrogen and it sees itself bonded to another hydrogen. What the picture doesn't really show you is that water actually has two pairs of electrons that haven't been bonded with anything. And it's because of this non-bonding, or these two non-bonding electron pairs, sometimes we call these lone pairs of electrons, that's what causes the net negative charge on top of oxygen, and that's why it's polar. Same idea with ammonia. It actually has two or one lone pair of electrons, and so that actually makes it net negative overall. If you have a look at BF3, okay, for boron, it's net positive at the middle. It bonds to fluorine, fluorine, and fluorine only. There is no other sets of lone pairs of electrons, so overall it's symmetric. So that's why it has a net dipole of 0. It's nonpolar. Same thing with methane. Okay, so carbon and hydrogen have a big difference in electronegativity. So there is that kind of difference between the bonds. However, because carbon is just bonded to hydrogen in all directions, it's symmetric. So basically, the positive charges cancel each other out. So again, they also have a net dipole of 0. So it's also nonpolar. If we put this on a chart now that we know what covalent polar compounds are, and then we compare that to covalent nonpolar, and then we compare that to ionic, this is the kind of chart we're looking at. So from 0 to about 0.4, most of these kind of covalent compounds are nonpolar. So electrons will be equally shared. From about 0.4 to about 1.8 or even 2, okay, from here, it's still going to be covalent. So it's still going to be between mostly nonmetals, but it is polar, which means the electrons are now being shared unequally. That's what we see here. Anything beyond 1.8, okay, it's just electron transfer. So here we have positive and negative particles. So we have now positive, negative particles. While as this one, okay, we have partial charges, which are not particles. Okay, it just means more electron density on one side of the molecule. Okay, so it's not a particle in that sense. Now let's have a look at the types of inter and intermolecular bonds. So we have a thing called dispersion forces. We have a thing called dipole forces. We have a thing called ion dipole forces, and we have a thing called hydrogen bonding. So we're going to look into these, okay? All right, firstly, let's look at dipole forces, okay? Now this goes back to what we were talking about, polar molecules. So when we're drawing this out, we said hydrogen doesn't really attract a lot of electrons towards it, so it's got a net positive charge. Chlorine wants to take as much electrons as possible, so it has a net negative charge. Okay, and so if hydrogen chloride, or hydrochloric acid, we sometimes call it, if this particular chloride is then placed near another hydrogen chloride, it's going to, because this is a negative and then hydrogen is a positive charge, they're going to try and attract towards each other because there's a net charge difference. You might remember this type of force. We call this electrostatic. So positive charges want to go to negative charges. In this case, we have a partial charge wanting to attract to another partial charge. Okay, so this is what you kind of see. So it kind of migrates across like that. Okay, so polar molecules can align with each other. The positive end will always close to the negative. So that's what you can see in this diagram here. If they keep repeating this pattern, so they keep making these dipole forces, okay, then they make a big network, and that basically determines the boiling point and melting point of the molecule. So if you have lots and lots of dipole forces holding a molecule together, you're going to increase the overall melting and boiling point. And this is another showing for dipole moment. You can see how this oxygen here is taking a greater amount of the net electrons. Same thing here. And then you can see here where the atom is asymmetric, or not asymmetric, symmetric. You can see that it's overall distributed equally, and so there's no dipole moment. So, like I said again, asymmetric dipoles. Okay. So there we have that. The other thing that does affect the dipole forces is how polar the molecule is. So the greater the polarity, okay, also the stronger the dipole forces. So if one particular molecule does take in more electrons than others, then that means that difference between positive and negative charges is a lot bigger, which also means that you will get a stronger attraction force between the different types. Remember, partial charges only. Let's try and compare the boiling points. So you have methanol, which is a polar or has dipole forces, dipole moment as well. And then you have ethane, which is nonpolar. You can see there is a gap in their boiling points. Okay, so the nonpolar is a lot lower in boiling point. You can then again compare the structures here. So hydrogen sulfide, you can see that based on this diagram it's showing you, there's a greater electron density on the sulfur in comparison to the hydrogens, whilst methane, the electron density is shared very equally, and so that kind of shows the difference in boiling points and in terms of the amount of polarity between these particles. Okay, so if we do a quick recap of what is a dipole force, okay, it is a permanent dipole moment. So you have permanent negative and positive charges that are attracted towards each other. If you have a greater difference in electronegativity between the elements of that polar molecule, you're going to generate a stronger dipole-dipole intermolecular force. Okay, so there's that. What physical properties does this provide? Obviously, if you have a stronger dipole-dipole force, you have a higher melting point and boiling point of that particular substance. Then we're going to look at the weakest types of intermolecular force. Now, you might hear it by different names: dispersion forces, van der Waals forces, London forces. To be honest, I don't really have that research done of why there's 3 different names, but there are 3 different names. Okay, look at this image here, and that might give you a little understanding of what we're about to talk about. Okay, we have 2 atoms or 2 elements moving towards each other. As one is moving towards the other, you can see the electron cloud here is pushing the electron cloud here away. Okay, so it's pushing the electron cloud away. Now, what we know when we just talked about all this is if the electron cloud is moving closer to this left-hand side here, we're developing a partial negative charge, which means what's left over here is a partial positive charge. Okay? So if we have a partial positive charge, okay, this atom will then develop a partial negative charge because it wants to attract to the positive charge, and so we're left with a partial positive charge on this end. Okay? Might be a little bit confusing how that all came to be, but again, look at this diagram here. As the electrons come closer, or as one atom comes closer to another, the electrons are going to repel against each other. So one side of the electrons will try and move as far away to one particular corner of that element. And so that's where majority of the electron density is. That leaves the center of that atom being relatively positive. So that gives it that partial charge. If we have a partial positive charge, that means any electrons in the incoming particle will try and migrate closer towards meeting this positive charge. So if all the electrons in the second element is trying to move to this particular positive charge here, that leaves you another net positive on the opposite side. And that's how dispersion forces work. It's by using this temporary change in polarity to attract elements together. Okay? So this is just like a little summary. So electron cloud from molecule A will repel the electron cloud from molecule B. So that's what you're seeing here. One side becomes more positive, one side becomes more negative. This causes a temporary dipole moment with the other molecule as well, causing electrostatic attraction. Okay, so this is electrostatic attraction here as well. All right, so what can you do to increase the dispersion forces? One you can have is a higher atomic mass, so an element that's technically more heavy. The reason that being is if the atom is bigger, it will have more electrons, so a larger electron cloud. That means that there's a greater difference in temporary dipole. So that really helps. As you can see, from fluorine to iodine, we are increasing the amount of electrons. And so we're seeing an increase in the amount of boiling or the temperature for boiling to occur. The other thing that does also count is the how compact the element or the compound is. So if they have the similar mass, so butane is CH10 or H10, and then we have 2 methanol propane, which is again C4H10. So they have the exact same structure, but as you can see, okay, this compound here is less dense than this compound here. So this compound is way more compact, which means the electron clouds are less dense, and so that reduces the overall dispersion forces. Because the electrons here are spread out a bit more across the molecule, it allows for greater dispersion forces to be created. Okay, so this is just a thing for you to copy later on. Remember, dispersion forces provide a temporary dipole moment, unlike the dipole-dipole, which is a permanent. Okay, it is an attraction of a partial negative and positive charge. If you increase the atomic mass, electron cloud, or ensure that the structure is less dense, so less compact, then you'll see a stronger dispersion forces. The next one we have is an ion dipole force. Now, an ion, you would know, is just a charged particle. A dipole is just a polar molecule. So when these two come together, okay, the negative will try to combine with the positive dipole end, and the positive cation will try and bond with the negative dipole end. Okay. This one is something we see all the time. When you put a ionic compound and try and dissolve it into water, this is what's actually is happening. So you have sodium, or you could have sodium chloride, which is the positive ion, which we have here. Okay. Now the water, oxygen is the partial negative charge. So water will latch on to the sodium ion and displace it from its ionic lattice. So that's what its function is doing. So this is what's happening here. So if you're dissolving anything, okay, the ions, okay, will be taken out of solution by the polar molecules, and usually we have here, just give me a second. Okay, so what I was trying to say here is the way it works, we call this thing dissolution. So when an ionic compound goes into, let's say, water, a process called dissolution occurs. So each individual ion, being negative or positive, is going to be removed by the polar molecule in that solvent. And the way it works is, like I said, the positive charge is going to be taken away by the negative end of the polar molecule. The negative charge will be taken away by the positive end of that molecule. Okay, so that's basically ion dipole forces, and they are basically just, again, electrostatic attraction. The last one we're going to look at is hydrogen bonding. Okay. Now, hydrogen bonding, by its name, is to do with bonding with hydrogen atoms, but there's a slight extension to that, and that's the factor where this type of bond is only applicable to oxygen, nitrogen, and fluorine. Okay, now some of you might think, why is it only applicable to these atoms, even though other elements will bond with hydrogen? And that's because of the amount of electron deficiency in the hydrogen. So technically, after bonding, hydrogen doesn't have any more electrons, so it is a net positive charge. But it also has to do with the amount of electron pairs remaining on the oxygen, fluorine, and nitrogen. Okay, if you look at the two examples I've shown here, we have nitrogen here with hydrogen. So these are the two things I've made. I've made water, H2O, and I have ammonia, which is NH3. If you can actually have a look here, water has two electron pairs remaining. So there's two, okay, electron pairs, whereas nitrogen has one electron pair. So these lone pairs of electrons, okay, increase, okay, the amount of electronegativity of the oxygen here and the nitrogen here. And so it creates a really strong polar or dipole moment again. So, be it all, at the end of the day, hydrogen bonding is just a really, really strong dipole-dipole moment. And that dipole-dipole moment comes in the fact that hydrogen is very electron deficient, and oxygen, nitrogen, and fluorine have lone pairs of electrons that make it more electronegative at the center. And we can actually have a look at that in terms of their boiling points. So see here, H2O, that is an example of hydrogen bonding, HF, hydrogen bonding, and H3, hydrogen bonding as well. Obviously, it's not the only one. So water, it has hydrogen bonding, it has dipole-dipole, it also has dispersion. So it has all three, okay? While as something like hydrogen sulfide, that's only dipole-dipole and dispersion. So that's why you see that sudden drop in boiling point in comparison. And then you have methane here, which doesn't have dipole-dipole or hydrogen bonding, and it's only got dispersion forces. Okay, so you can see the difference where one particular compound has all three of these intermolecular bonds between that compared to another compound which only has two of them, and then the last one, which only has the weakest intermolecular bond, has also the lowest boiling point based on their position on the periodic table. So they're the strongest diable bonds. That's basically what you need to know for hydrogen bonding. Last thing we're going to talk about is just the strength. So dipole has, or iron dipole is the strongest. The weakest is dispersion forces. If we look at this in terms of the energy between the bonds, so this is just the energy of the bonds. Iron dipoles, the strongest, about 40 to 600 kilojoules. Okay. Hydrogen bond, 10 to 40, dipole, 5 to 25, iron dipole induced, So this is just a special case of dispersion with this bit here. And then you can see dispersion forces, obviously the weakest one out of the lot. If we then compare our inter and intramolecular bond strengths, iron on iron, so positive charge, negative charge, they will produce the strongest amount of energy per bond. Then you have the covalent bonds, so these are your intramolecular bonds. So that's why splitting elements inside an atom is so difficult, because they actually require the most amount of energy to break apart. They have the most amount of energy as well. Intermolecular bonds are a lot weaker. That's why you can boil things, you can freeze objects like that. And this is the range that they have, with iron dipole being the strongest of the intermolecular bonds, and then dispersion forces being the weakest of the dispersion of the intermolecular bonds. Okay, and so that's basically it of what you need to understand about inter and intramolecular bonds. Okay.